Have you ever stopped and thought about what it takes to build those tiny little computer chips?
The ones that powered practically everything.
Yeah. I mean, it's
Yeah.
kind of like building a skyscraper, right?
Mm-hmm.
Billions of components,
Right.
intricate layers.
Yeah.
And it all has to connect perfectly.
Mm-hmm.
But we're not talking about steel and concrete here.
No.
We're talking about microscopic transistors.
Right.
And that's where things get really interesting.
Yeah.
So in today's deep dive,
Okay.
we're going to be looking at some excerpts about computational lithography,
Okay.
which is like the secret sauce behind making these chips.
Interesting.
And I know you're especially keen on understanding how companies like ASML
Yes.
achieve this mind-boggling precision.
Oh, you are in for a treat.
Okay.
Because grasping the actual processes involved is
Yeah.
like peeking into a world where the line between science and magic,
Right.
it just gets blurry.
Okay, so first things first.
Yeah.
We're dealing with features on these chips
Uh-huh.
that are measured in nanometers.
Nanometers.
Can you even picture that?
It's mind-bogglingly small.
It's like trying to perfectly align grains of sand,
Yeah.
but 1,000 times smaller.
Exactly, and that's the challenge, right? That keeps chip makers up at night.
I bet.
Because as we demand more powerful devices,
Mm-hmm.
the features have to shrink.
Yeah.
And so it's constantly pushing the boundaries
Yeah.
of what's physically possible.
So it's like this never-ending race
It is a never-ending race.
to make things small
To smaller and smaller.
and smaller.
Yeah.
Okay, so where does ASML come to play
Right.
in this nanometer-sized showdown?
So ASML plays a critical role
Okay.
because they provide the lithography systems,
Okay.
which are like the super advanced 3D printers of the chip world.
Okay.
But they also develop the software
Uh-huh.
that drives the whole printing process.
So they're not just giving you the tools.
You know.
They're giving you the instruction manual, the troubleshooting guide,
Right?
the whole 9 yards.
The whole 9 yards.
Yeah.
They've married this deep understanding of how lithography works
Okay.
with this cutting-edge software to
Yeah.
optimize every single step
Wow.
of chip creation.
Okay.
But before we get ahead of ourselves,
Okay.
let's make sure we're all on the same page.
Yeah, that's a good point.
How does lithography even work?
Yeah, it's easy to get lost in the weeds if we don't have the basics down.
Absolutely.
Yeah.
So imagine shining a light
Okay.
through a blueprint,
Uh-huh.
which we call a mask,
Okay.
onto a silicon wafer.
Right.
The light that passes through creates a pattern
Okay.
on the wafer.
Got it.
Think of it like using a stencil
Yeah.
to create a design.
Like arts and crafts.
Yeah, exactly, like arts and crafts.
Okay.
But on a microscopic level.
So far, so good.
Yeah.
But I'm guessing
Mhm.
that things get more complex at the nanoscale.
Oh, absolutely.
Right. You mentioned you were particularly curious about how ASML
Right.
achieves such precision.
Yes.
Are you starting to grasp
Yeah.
the complexities involved here?
Definitely. At such tiny scales,
Uh-huh.
various physical and chemical processes
Okay.
come into play.
Right.
And they cause distortions in the patterns.
So it's not as straightforward
Yeah.
as just shining a light for a stencil.
It's not that simple.
Okay.
Imagine projecting a perfect image
Okay.
through a slightly warped lens.
Yeah.
The image wouldn't be quite right.
Ah, I see the problem.
Yeah,
It's like trying to draw a straight line
right.
on a bumpy surface.
Exactly.
Okay, so how do they address these distortions
Right.
and get that perfect print?
This is where computational lithography takes center stage.
Okay.
And this is where ASML
Yeah.
really flexes its technological muscles.
Okay.
They use these incredibly complex models and algorithms
Wow.
to predict these distortions, and then they adjust the system to compensate.
So it's like having a microscopic self-correcting mechanism
Exactly.
that's constantly tweaking things
Constantly
to
tweaking.
ensure a flawless image.
A flawless image.
That's incredible.
It is pretty remarkable.
So it's not a one-and-done adjustment.
No.
They're constantly monitoring and tweaking things.
Yeah, constantly monitoring and tweaking on the fly.
Wow.
And they've got different tools for
Yeah.
different types of optimization.
Yeah.
Take source optimization, for example.
Okay.
This involves adjusting the illumination source
Huh.
to produce sharper images.
Okay.
Think of it like fine-tuning a spotlight.
Okay.
to perfectly highlight an actor on stage.
That's a great analogy.
Yeah.
So they're manipulating the light itself
Manipulating the
to
light.
get the best possible print.
Exactly.
What other tricks do they have up their sleeve?
Well, they also use mask optimization techniques.
Okay.
Like you may have heard of things like optical proximity correction, or OPC,
Right.
and inverse resolution enhancement technology, or IRT.
Okay.
These techniques involve designing masks
Uh-huh.
that compensate for optical effects.
Okay.
So ensuring that the patterns print exactly as intended.
So they're essentially outsmarting the distortions
They're outsmarting the distortions
before they even happen.
happen.
That's some next level thinking.
It's pretty amazing.
You mentioned wavefront optimization earlier.
Yes.
What's that all about?
That's a crucial one.
Okay.
Because heat
Yeah.
generated by the light
Uh-huh.
can actually deform the optics.
Really?
Yeah.
Oh, wow.
So wavefront optimization tools
Okay.
reshape the light to counteract those deformations
Okay.
to ensure accurate printing.
So it's like having a system that constantly adjusts for
Yeah.
tiny tremors in the printing platform.
It's like that, but instead of a tremor,
Right.
we're dealing with changes in the refractive index of the lens
Okay.
due to heat, a concept that is fascinating in its own right.
Wow. The level of detail they have to consider is
It's remarkable.
mind-blowing.
It is.
And to think
Yeah.
these adjustments aren't just happening once.
No.
They're happening pattern by pattern, layer by layer,
Right.
chip by chip,
Chip by chip.
wafer by wafer.
Wafer by wafer.
It's crazy.
A lot.
It's a lot to think about.
It is.
It makes you appreciate the incredible ingenuity
It really does.
behind the technology
Absolutely.
we rely on every day.
Yeah.
We've gone from skyscrapers
Right.
to microscopic transistors.
Yes, yeah.
We've gone from blueprints
Uh-huh.
to self-correcting systems.
Right.
And it's clear that computational lithography
Yeah.
is a true marvel of engineering.
A true marvel of engineering.
But this level of precision,
Right.
it begs the question,
Yeah.
what are the limits?
I have the limits.
Will we reach a point
Yeah.
where transistors become so small
Yeah.
that even the most sophisticated computational lithography can't keep up?
That's a good question.
What breakthroughs
Yeah.
will be needed
Mm-hmm.
to continue this incredible journey
Right.
of miniaturization?
You have miniaturization.
These are the questions
They are big questions.
that will shape the future of technology
Absolutely.
as we know it.
That's it.
It's crazy to think
It
about.
really is.
I don't know about you,
Yeah.
but I'm blown away.
It is pretty remarkable
Yeah.
what they're able to achieve.
I know, it's amazing.
Yeah.
All right, well, that brings us to the end
Okay.
of this deep dive.
Great.
As always,
Right.
thanks for listening,
And thanks for having me.
and we'll catch you next time.
See you later.
Bye-bye.
Please like this video and subscribe to our channel. For more detail, you can visit our blog website www.evergreentechtips.com.